And then we move on to the last talk of this session. And this talk will be given by Yu-Xiong Wang, and is titled Adversarial Geometry-Aware Human Motion Prediction.
Thank you for the introduction. Hello, everyone. I'm Yu-Xiong from CMU. Today, I will talk about our recent work on adversarial geometry-aware human motion prediction. This is the joint work with my collaborators from CMU. Given a series of historical movements shown as a 3D black skeleton, motion prediction aims to forecast how a human moves or acts in the near future, shown as the blue skeleton. More formally, we represent human motion as sequential data. Our goal then is to find a predictor P that maps from the input sequence to the output prediction sequence. Prediction for less than 500 milliseconds is typically considered as short-term prediction, while long-term prediction focuses more than 500 milliseconds. Here, we address both short-term and long-term motion prediction. Human motion prediction has many applications in computer vision and robotic vision, such as human-robot interaction and collaboration, AR and VR, and motion generation for computer graphics and games. Driven by the recent advances in deep learning architectures and large-scale motion capture dataset, different learning-based approaches have been proposed recently. These approaches have significantly improved the prediction performance for a variety of tasks. However, generating human-like realistic motion is still a challenge. For example, here are some represented results from the state-of-the-art approaches, sampling-based loss and residual sweep. We observed that motion jumps or discontinuity between the prediction sequence and the input sequence. For a longer time horizon, the prediction even converges to some mean pose or becomes unrealistic. What causes such unsmooth, unrealistic prediction? One of the main reasons is that this previous approach only considered frame-wise correctness based on a Euclidean metric. The conventional Euclidean distance is commonly used as a loss to regress the prediction to the ground truth. However, it ignores the intrinsic geometric structure of motion frame and is thus not accurate enough. Moreover, only using frame-wise checkup cannot guarantee the entire generated motion is realistic. To address these issues, our key insights are twofold. First, considering that motion frames are represented as 3D rotations between joints, we introduce a geodesic loss to quantify the difference between the prediction and the ground truth. Second, we introduce, to achieve human-like motion prediction, we introduce discriminators as sequence-level checkup. Based on this insight, we modify the prediction framework as follows. An input sequence is fed into a predictor to produce the prediction. The prediction is compared with the ground truth using a geodesic loss. In addition, recurrent discriminators are introduced to deal with sequential data and distinguish between the prediction and the real future sequences. We will now explain each of these components. Following the recent work, we use a recurrent encoder-decoder based network for our motion predictor. The encoder consists of a linear layer and a gated recurrent unit, GRU layer, and takes the input frames sequentially to infer a hidden representation. This hidden representation, together with a seed motion, is then fed into the decoder, which consists of a linear layer and a GRU layer as well. Through feedback, the decoder takes its own output as the next time step input to produce the prediction. We now introduce a geodesic loss to regress the prediction to the ground truth. It is known that motion frames are represented as 3D rotations between joints, and the 3D rotation belong to spatial orthogonal group SO3. SO3 is a Lie group with a remaining manifold structure. It is thus natural to use the geodesic distance to quantify the difference between two rotations, which is the shortest part between them in SO3. More specifically, given two rotations, the conventional Euclidean distance is the length of the straight line between them, while the geodesic distance in SO3 can be defined as the angle between the two rotations. We represent the rotations with rotation matrix and use the logarithm map in SO3 to calculate the distance. We sum over all the joints and all the frames to obtain the geodesic distance. This geodesic distance, this geodesic loss works as a geometrically meaningful, more precise distance measurement at the frame level. How could we guarantee the entire generated sequence is realistic? Inspired by the adversarial training in GANs, we introduce discriminators as sequence level checkup. Different from the conventional GANs, we design our discriminator to be a recurrent network to deal with sequential data. The discriminator consists of a linear layer and a GRU layer, and it takes input sequentially to infer a hidden representation. And a fully connected layer with sigmoid activation then follows to output the probability the input sequence is real. We further designed two complementary discriminators. A fidelity discriminator DF distinguishes between short sequences, the ground truth, and the prediction sequence. A continuity discriminator distinguishes between long sequences by concatenating the input sequence with the ground truth or prediction sequence. Intuitively, the fidelity discriminator checks how smooth and human-like the prediction sequence is, while the continuity discriminator evaluates whether the prediction sequence is coherent with the input sequence. We use the standard GAN loss functions for our discriminators. By combining all these components together in an end-to-end fashion, we obtained our full model. During training, the predictor predict predictions from the input sequence based on the geodesic loss. The prediction and the ground truth are fed into the fidelity discriminator to evaluate the plausibility. Meanwhile, the concatenation of the input sequence and the prediction or ground truth are fed into the continuity discriminator to check the coherence. We integrate the GAN adversary losses and the geodesic regression losses and obtain the optimal predictor P star by optimizing this min-max objective function. Lambda is a trade-off hyperparameter that balances these two types of losses. During testing, we use the predictor P star for prediction, which has the same inference time as the previous work. We now evaluate our approach on the human 3.6M dataset. This is an important and widely used benchmark for motion prediction, which includes millions of 3D motion capture data for a variety of activities. We systematically evaluate our approach in both short-term and long-term prediction under different quantitative and qualitative protocols. Here we show some representative results. This plot provides the quantitative comparison with data of our RN-based approaches. The x-axis is time, y-axis is the mean angle error. The lower is the better. Ours consistently outperform these learning-based approaches in different time horizons. With longer time horizon, the improvement becomes more significant. We have also achieved similar improvement on other activities, which include in the paper. To understand the impact of different components and their combinations, we conduct detailed ablations. We can see that our geodesic loss is superior to the conventional Euclidean loss. This observation verifies that the geodesic distance is a geometrically meaningful, more precise distance measurement for 3D rotation. The two adversary discriminator further greatly boost the performance. Our full model consistently outperforms its variance in different scenarios, showing that different components are complementary to each other. Here we show some quantitative comparisons with state-of-the-art approaches. For example, the short-term predictions are shown as color skeleton and overlapped with the green ground truth skeletons. Ours is closer to ground truth with less jump. In longer time horizons, we can say that the prediction results of sampling-based laws converges to mean poses or drift away from the input sequence, making them unrealistic. However, our model produces more smooth, continuous, and human-like and realistic predictions. Finally, we conduct some user study to evaluate the probability of our prediction. Here we design A/B testing and pairwise evaluations. 25 judges are asked to watch randomly chosen pair of predictions and select the one that is considered to be more realistic and reasonable. The first row summarizes the success rates of our approach against the ground truth and baselines. We can say that ours significantly outperform the baselines and are comparable with the ground truth. To conclude, here we introduce a geodesic loss, which is geometrically meaningful, more precise distance measurement for motion frames. We also design recurrent discriminators and introduce adversarial learning for motion prediction and synthesized tasks. These components by themselves are general and can be potentially applied in other motion modeling and analysis tasks. At the same time, we have another ECCV work on few-shot human motion prediction via meta-learning, which aims to predict future motions for novel activities from just a few training sequences. Please drop by our poster for more details. One is this morning, and the other is this afternoon. Thank you for your attention.
Any questions?
Yeah, top left. Yeah, here. Oh, should I go ahead?
Yeah.
Thank you. Since your data set for learning is heavily dependent on the silhouette and landmarks of the human body, how does the human clothing affect the future predictions? Because it's based on geodesic. And number two is, can it be somehow extended for other type of animal motion or inanimate objects like cars or cloud motion and things like that? So there are two parts.
Okay, those are good questions. For the first question, currently we focus on like the single subject with clean background without any occlusions, because modeling human motion dynamics itself is a challenging task. I think it's worth exploring in the future how we could address like multi-object even with occlusion. For the second questions, I think from the approach themselves, they can sort of extend to prediction motion for other objects. Okay, thank you.
Did you check with clothing variations, how clothing variations on humans, does it affect the result?
Oh, we didn't check that, because for this data set, we didn't check for that. It's worth checking. Thank you.
Do we have another question? Yeah.
Sorry. So one problem that emerges with this geodesic loss is that some joint angles are more important than the other ones. For example, the root joint is a lot more important than the wrist. And moreover, sometimes this is a function of the action that you perform. For instance, if you are doing some acrobatic movement when you're upside down, now suddenly your wrist joint is a lot more important than the root joint.
Yeah.
So how do you think this affects the method?
Yes, that's a good point. Currently, we don't introduce additional weights for different joints, but definitely they have different importance if you're predicting different activity. We have ongoing work trying to address this kind of issue. Basically, we're trying to introduce some attention mechanism to automatically learn important parts and force a prediction. Thank you.
Okay, that ends this session. So let's thank all the speakers again.